Hello everyone, today I'm presenting my project for big data processing using Hadoop. My name is Muhammad Ali Ayub, RF analysis with Apache Spark. Okay, so the agenda for this meeting is we're going to first explain Apache Spark, then we're going to discuss some use cases. After that, we're going to discuss the domain of application, so basically where I apply Apache Spark. And then we're going to look at the demo, and then we're going to talk about challenges or lessons learned. So what is Apache Spark? So from the Databricks website, which is a provider of Apache Spark solutions, they provide a cloud-based hosting solution for Apache Spark. Their website states that Apache Spark is a lightning-fast unified analytics engine for big data and machine learning. It was originally developed at UC Berkeley in 2009. And that pretty much does sum up what Apache Spark is. It allows you to cluster computing on large data sets, and you can do all sorts of analysis based off of machine learning, big graph data analysis. There are a lot of cool features that Apache Spark provides. So it can run in three modes. We'll talk later about that, and it's trusted across many different industries actually, and there are many contributors in terms of development for Apache Spark. So on the right-hand side, you have cluster management in Apache Spark. We already kind of talked about how there are three modes or architectures. We'll get into more detail later, but essentially you have a standard standalone cluster, you have Apache Mesos, and then you have Yarn. And then on the bottom right, you can see the Apache Spark ecosystem. So let's describe that a little bit. Essentially, Apache Spark Core, it has many different APIs. So you can use R, SQL, Python, Scala, and Java to essentially talk to the Apache Spark framework, excuse me. And so you have a Spark SQL, you have Spark Streaming, which is essentially real-time streaming of large data, and you have MLlib. That's the library that I used for my project. And then you have GraphX, which is graph computation, and then finally you have Spark R, R on Spark. In case you're not familiar with R, R is another programming language. It's heavily used by data scientists and statisticians. So as you can see, the Apache Spark really does try to cater to the data scientist. You have R, you have Python, and actually can serve data analysts as well from SQL, Scala. Scala is for more software development, and so is Java. But yeah, it serves many different purposes. Okay, so where does Apache Spark, well, where is it useful? It's actually useful in many different locations. Desire, so the image you see on the top left, it was created by Desire. And well, there are many different applications. Anywhere you can think of with large data sets that require massive processing, you think about Apache Spark, you think about Hadoop MapReduce, you think about some of the other big data frameworks out there. Now, Apache Spark really does take the cake because it does something, well, it does most of its analysis in memory. And we'll talk a little bit more about this later, but if you look on the right-hand side of the screen, Apache Mahout does machine learning and uses the hard disk. So that's another big data framework. It's part of the Hadoop ecosystem, really. And then you have Hadoop MapReduce, which allows you to process data, but again, it hits the hard disk essentially. And Apache Spark is much faster because it uses the memory. So it will think of like a cluster that you set up. You can actually store the data in a replicated fashion, in a resilient fashion across many different servers in the memory, in the RAM. And it has many different APIs. It has Python, Java, Scala, and R. And then they have many different types of data structures, like data frames. So think of your Python pandas data frames. It's a similar API. And then you have RDDs, resilient distributed data sets, the stuff that I was talking about. So this is essentially when you can put your data in an RDD format. There's replication involved, there's distribution involved, and basically Apache Spark takes care of your data for you, so you can analyze it. So yeah, finance, retail, travel, media, healthcare, all sorts of industries are using Apache Spark or can use Apache Spark. All right, so real quick terms, definitions related to Apache Spark. Not going to go through all of them here. Actually, as a matter of fact, really the only one you want to be concerned with is a job. So the bottom, you have a parallel computation consisting of multiple tasks that get spawned in response to Spark action. And you'll see this term used in the driver's logs. Of course, everything here is important, but in general, I leave it up to the audience to revisit the slides really, and then you just have the application really. That's so I'm going to demonstrate an application later, so it becomes a lot more concrete. But Apache Spark allows you to write your code in a different language, R, Python, Scala, what have you, and then you can execute it using something called the Spark context. And the Spark context allows you to actually talk to the underlying distributed framework. And we're actually going to talk about that right away, right next. So, um, programming for Spark really, you have a couple of things, right? So, like I said, you have your program. You can write it in whatever language you find comfortable to write your software in, and that's going to have the Spark contract context, and it's going to be talking to the cluster manager. So the cluster manager, you have three different types of setups, and essentially at the very end of the day, like you have worker nodes, they have executors, and each executor can be doing all sorts of tasks really on the cache. And you think of cache, you think of in-memory data storage. So the program flow is left to right. You will have a bunch of commands that you want to run, and the data is stored in a distributed fashion. And you're going to use the Spark context, and that's going to feed into the cluster manager. The cluster manager is going to dish out that work to different cluster nodes. Now, a very important thing to remember here is Hadoop, Spark, what's the relationship, right? So Hadoop is a very good place or very good way to store large data sets, especially because of HDFS. It's a proven technology. Now, the thing is, some people might say Hadoop is, it's Hadoop and Spark are basically they have to be used one or the other. Actually, there are other articles that would say that really they're actually very much complementary. So you store your data on Hadoop, but then when you want to do processing on it, you can use MapReduce, but you can also use Apache Spark, and it'll take that data, it'll store it in RAM, and the reading from the CPU to the RAM, it's a lot faster than it is for hard disks. So that's why when I was mentioning Apache Mahout in this slide and Hadoop MapReduce, see, those are very, very powerful frameworks, but they still utilize hard disks. And so does Apache Spark, but Apache Spark is designed for optimization and it can read data much faster. So let's go back real quick. Like I said, there are three types of cluster setups. Let's talk about the standalone architectures. So this is a type of architecture you can see on the right-hand side. You have a master node. You're going to have slaves on the right, and these are going to be fanned out on different servers. And each one of them is going to have memory, and they're going to be performing work. Now, these are simpler deployments. So Apache Spark basically, this is a standalone deployment. It allows you to do a simple deployment, and you can hand configure many of these like servers individually to do the standalone architecture. Now, this is very useful for testing purposes, getting your feet wet on the technology, and essentially learning a lot, and also kind of experimenting with data. In production, you can use the other two formats as well, which are very powerful. And like I said, last bullet really, one machine or a handful of machines, you can run it the standalone architecture. Okay, so let's talk about the second type, and that's the Yarn Resource Manager. So Yarn, we're very familiar with. So Hadoop really, you use HDFS underneath the hood, and essentially, if you look at the screen on the left side, so the image, you have the client. It's going to dish a request to the resource manager, and I mean, also at the same time, look at the application masters on the bottom left. The application master is taking care of map tasks. So the very left, bottom left of the large blue, dark blue rectangle. And then on the right rectangle, you have a reduce task. So the application master is taking care of all of that, and all of that's confined within the node managers. So we're familiar with this from class, but then you can analyze and you can leverage Hadoop using Spark, Apache Spark. So the last architecture is Apache Mesos. Apache Mesos is a very, very powerful framework. Yeah, so the second bullet there, it allows for scheduling at the OS level, and I'll get a little bit into that, but it's a resource manager that provides grained sharing and two-level scheduling. So these are different capabilities that it provides, and yeah, so it's the Apache software framework. If you look on your right hand side, so that right graphic, so it's just some of the things to mention here. You have the Mesos master in the center, and you have Mesos agents. These agents software is distributed across a cluster, and they will execute stuff for you. So I mean, without getting into too much detail, each of these agents can actually provide a lot of information about the types of resources they have available. So, for example, an agent might publish that it has two CPU cores, it has 4 gigabytes of RAM, it has 500 gigabytes of solid state memory, hard disk memory. So it can mention that. And so if you look at the left hand side, over here we see that the Mesos master, you have a couple of messages being passed around. You have two agents, one's grayed out on the bottom, and then agent one is not grayed out. And you can see the types of essentially tuples or tuples of information. So like if you look at the message one, it'll say, resource one, and you have 4 CPU, you have 4 gigabytes. All of this information is being essentially passed around. And what you're doing is, if you have a workload of some sort, you're able to efficiently distribute the workload because you know what resources are available at what nodes. And you have two frameworks running. So Apache Mesos is very, very powerful. Now, for my demonstration, I decided to use the standalone architecture. I wanted to, get my feet wet with Apache Spark, but at the same time, do somewhat of like a very cool RF design experiment that leverages big data and shows that you can use big data techniques with RF data. And I'll talk a lot more about that actually now. So, demo explanation. So we've talked a lot about Apache Spark and its use cases, and you know, I work with RF in the field of RF, and it's RF stands for radio frequency. So I had this project idea essentially to see if I can use big data technologies on RF. Now this is not a new idea, but I wanted to do some sort of machine learning algorithm using Apache Spark, using in particular the MLlib library or software, and then doing some sort of analysis on the RF data. So what exactly is a radio frequency? If you look at the very left, you see these waveforms, right? And it says low frequency, high frequency, ultra high frequency. So, the world we live in, we have electromagnetic waves all around us. You have red, green, blue, Roy G. Biv, essentially the colors that we see around us. That's an electromagnetic wave. You have the sun's rays, those are EM waves. You have gamma rays, you have X rays, etc., etc. Now, it turns out if I want to communicate with someone, my cell phone will have a circuit inside of it, and it's going to essentially uh, flow electrons through the wire and, well, through the antenna, excuse me. But the electrons are gonna flow through it, and they're gonna go back and forth in a sinusoidal fashion. Now, with the antenna, you're gonna end up releasing electromagnetic energy, essentially a wave, and you can model that wave, that physics phenomenon, using just sine and cosine waves. And so, that's on the left-hand side. If you look at the second graphic from the left, you see that you have a circuit diagram right here. And if you can see my cursor, you have the D to A, that stands for digital to analog. So essentially your cell phone, your computer, your tablet, what have you, they're going to take that data, they're going to convert it into something called analog waveform. Basically, they're going to convert it to a bunch of like different voltages and ampages. That's going to be modulated. So you're going to encode that information. You're going to mix it with some sort of carrier. And I mean, there's a lot that goes into this, but at the end of the day, you're using circuitry to essentially transmit information across the channel. Now, you might be wondering, how exactly do you transmit information, right? Because we said that we can model electromagnetic waves as sine waves or cosine waves, essentially sinusoidal waves. If you look at the third graphic from the left, if I have a wave with a certain frequency and I want to transmit ones and zeros, I can turn it off and then I can turn it on, then I can turn it off and turn it on. This is called amplitude shift keying. It is one way that you can transmit ones and zeros from one source, so one cell phone or one Bluetooth signal, provider or essentially transmitter to another receiver. And so what you're doing here is the receiver is going to be listening. It's going to be tuned in to that frequency. So like we said, there are different sinusoidal frequencies in the air, just in the air, in the electromagnetic spectrum, and you're tuning into specific ones. And really, that's how everything talks. If it's wireless, you're doing some sort of modulation, and you're using sines and cosines, and it's all embedded in the circuitry. And so this is what we call radio frequency in terms of essentially digital communication theory, right? And the big takeaway from here is RF is very important. RF engineering is very important. Everything around us uses RF engineering in one shape or another, essentially. So now that we've talked about how important RF engineering is, let's imagine a scenario where you have four transmitters. So let's just say you have an Internet of Things setting in the house. You have four transmitters, and they can transmit. Now they could transmit on different frequencies, and the signals they send are going to be slightly different. And there's one receiver that's basically listening in the environment, and it needs to essentially classify whether or not, for a certain time frame, if a particular message is of a particular transmitter type, because it only wants to listen to transmitter A. So of the four transmitters, when it's reading in data just from the environment, it wants to classify each data packet that comes in. It wants to classify it as transmitter 1, 2, 3, or 4, and then based off of that, if it's transmitter 1, it wants to read that information. So in this, it's a bit of a contrived example, but there are similar situations that might arise in the real world. And so that's the kind of project or a demonstration I wanted to use Apache Spark for. So the first thing was, data collection. I actually built my own data set. I used something called GNU Radio, and I'm not going to get into too much detail. OFDMA is essentially a multi-access protocol. It's very complex. At the end of the day, essentially, it allows you to transmit information on across different frequencies across time. If that doesn't make sense, it's not necessarily important for the purposes of this presentation, but basically at a high level, if we look at this diagram, this is a simulation that I set up. The block diagrams actually, this actually is part of the software GNU Radio, and it'll generate the data set. So in the orange, you have your four different waveforms. And then in the gray box, you can see those waveforms are being added. So they're being added, and then they're going to be multiplied, and then added again and subtracted. Essentially, you're coming up with your signals and you're modulating them. Modulation being like you're changing them to transmit ones and zeros. And then the signals come out of the gray box. They go in, and then the yellow box says noise source. So it's going to add in noise and to simulate the real world scenario. And then you're basically file syncing out two of them, meaning you're writing that data to file. So I wrote the data that's directly coming in from the gray box, and then the data that's coming in from the green box, but it's being added, noise is being added to it. And that's in the second file. The reason why I did this is just to look at some of the clean data, but in reality, most systems you're going to encounter all sorts of noise in the environment. So, the demo is going to actually, you're going to train machine learning models on data that has noise in it. And essentially, it needs to be able to classify what transmitter was sending the information. Okay, a little bit of subtlety here. I'm not actually sending ones and zeros. I'm more just choosing on the frequencies and the time periods when those frequencies are used. It's not necessarily important for the big data project, but feel free to contact me if you want me to discuss more in detail how and what I did to generate the data. Now the data, it came out to be 200 to 400 megabytes. So I had two data sets, one at the 200 millivolt noise range and one at the 400 millivolt noise range. Basically, all you need to know is that I have two data sets. One has less noise and one has more noise, and so my machine learning algorithm should perform worse on the larger noise. Essentially, it's harder to classify signals with a noisy environment. And there are four types of signals. Like I said, at the very top, you see the table. So for time slot 1, 2, 3, and 4, you're going to be transmitting, for example, for 1, you're going to be transmitting 20 kilohertz wave with amplitude 2 and 15 kilohertz wave with amplitude 1.5. And I'll show you what that means on the next slide. So these are some samples, and you can look at the very top right. You see there are 4 sample types. You have class label 0, class label 1, class label 2, and class label 3. Each one of them is one transmitter, essentially. And you have 2 frequencies present that are being modulated. So if you look on the top left, you see the clean data. If there was no noise, this is what it would look like. And you can see the pattern clearly. It repeats itself every 4. In the real world, you might not have that kind of repetition. It's just for my data generation purposes. In the real world, the receiver would try to figure out, every 0.0005 seconds, it would try to figure out which one of the transmitters was talking at that time. So the clean data looks like it's above, like it looks easier to classify, and it really is. But the realistic data is with noise added. So you can see that same data that we see, it's been added, it's been essentially corrupted a little bit. So it's going to be harder to classify. Okay, so let's move on to the algorithms used and results. So we use 2 algorithms from the MLlib. Well, I use 2 algorithms from the MLlib library, and you have essentially 2 ways to compare them. So the classification algorithms were naive Bayes and decision trees. Naive Bayes is a classification algorithm. Decision trees are another classification algorithm. Not necessarily important for the purposes of this meeting or this presentation, but basically we can compare their performance with something called a confusion matrix, and I'll explain in a little bit more detail what that is. So actually looking at the bottom right, we have the performance of naive Bayes. So for the 200 millivolt data set, so essentially 200 millivolts of noise, you have the confusion matrix right here. And it's the second one from the bottom right. So it says below is the confusion matrix, naive Bayes tree. And the way you interpret this is each row is the label, and then each column is the prediction. So basically, if you were to sum across the first row in that table, you see that the sum is 9,543 data points for row 0 or row 1, right? And that means label 1, you had 9,543 training labels, and well, test labels actually. And then basically from there, you'll notice if it's a column wise, of the 9543, you actually labeled all 9543 as class 0. So essentially then, of all the 9,473 that were labeled 2, so class 2, all of them were labeled as class 2. So the idea is you want to have a matrix with only diagonal values filled out. That means it has 100% accuracy. So in particular, naive Bayes, for the 200 millivolts of noise, it performed 100% well, and then like accuracy wise. And then the second 400 millivolt noise, so this is a more noisy environment, it still performed very well. Conversely, basically the decision tree algorithm, I on purpose for demonstrations at least, I use the decision tree algorithm, but this is a little bit specific to the algorithm. I decided to make the branching factor a lot smaller, and so because of that, the decision tree algorithm could only learn a limited amount of information from the training data. So for the 200 millivolt data, it guessed, you can see the diagonal matrix, so it got everything correct. It was 100% accurate. But then the second matrix from the top, you see that confusion matrix for the decision tree. You can see that, if you had 16,624 total, if you were to sum across the first column, and what that means is you essentially had for this. So another way to phrase this real quick, if you look at the first row, actually, I'm sorry, you have 16,624 labels, and they're all labeled class 0. So you have 16,624 class zeros. But of those 16,000, you actually labeled about 79, about three here, 79, and 62 incorrectly. And so then if you look at the perfect scenario, you have 16,593 class 1. And so class 1 over here, of those 16,593, you labeled 66 to class 0, 11 to class 3, sorry, 26 to class 3, and 11 to class 2. So bottom line is the decision tree didn't perform as well. And so Apache Spark was able to leverage the big data cluster that we set up, and it was able to, and again, I set up that cluster in Databricks. So Apache Spark was able to I was able to leverage Apache Spark for decision trees and naive Bayes classification algorithms. All right. So again, to set up the data and to store it and to data engineer everything, I use Databricks. I'm going to show everybody what that looks like. After collecting the data, we had to feed it into the MLlib framework. So let's go ahead with a demo. So the demo is already set up for us over here. So over here, you can see it's a notebook. This is like a Jupyter notebook if you're familiar with. So So over here, we can see the Jupyter Notebook. It's similar to Jupyter Notebook if you're familiar with what that is. And essentially, I have my code written in blocks, and I can execute my code. My code is using the RF machine learning cluster. It has 6 gigabytes of RAM. It's actually not running on it's only running on one machine from the looks of it. And you can actually detach clusters. You can assign a cluster a bunch of jobs. And so I have this one cluster, and I have this code. It's going to be reading in the data, it's going to be data engineering, and then it's going to use machine learning models. I'm actually going to execute some of this for us right now. Now, some of the models can take some time to train, so I'm going to only show some of the stuff that I can do real time. So in this scenario, I've already uploaded my CSV file. So with noise, 400 millivolts of data added, noise added. So if I were to run this, I'm going to press Shift Enter, and then it sends it to the cluster, as you can see over here. Now, while it's sending to the cluster, it's after it's done sending to the cluster, it's going to show us the results. And also, in real time, kind of shows you, the jobs that are executing and how well they're doing, and then you can get more information on this on the status of these jobs. Now, it looks like it finished up. If you look at the data frame, I'm actually going to display all columns. So like I said, each label is a series. It's basically a vector of time data points. So C0, and if I go all the way to the right, I have 50 data points, 0 to C49, right? So C0 to C49, that's 40 data points. So it's basically a time series data set, essentially, and then the label is C50. So 0, 1, 2, 3, 0, 1, 2, 3. And so I have a bunch of data. This is only showing the roughly top 10 top 10 rows, top 1,000 rows, excuse me, right here. I can scroll through my data, and I can even graph it and plot it if I wanted to kind of visualize it like I showed in the slides. Okay, the next thing is then, once I've done that, I actually wanted to convert typecast. So this is part of the data engineering process. I converted each type to double. So I converted all the columns to double because they were string. And then the last column, which actually had the truth label, I converted that to integer type. So over here, I can run this actually. Press Shift Enter. You're sending it to the cluster. And once it's done executing, you see the same exact data, but now the data types are different. And so you can actually do machine learning with this double and integer type data, not with string data. So scrolling down, this is how you can save the data to a view or a table. And then you can use actually with %SQL, you can actually just start using SQL commands on that data set, on that table once you've created it. So it's very useful. I'm not going to demonstrate that right here. I'm actually going to go on to the machine learning part. Again, before we do the machine learning, we want to get some statistics on the data. So if you can see over here, this code would generate some high-level statistics. The data generated, this is kind of messy. So what you can do is you can actually copy and paste all of it, and I have it copied and pasted right here. So you can see you have the summary for each column. It gives you the count, how many there were, mean, standard deviation, min, max. So Apache Spark can let you do that really quickly on these large data sets to get an idea of just what the data looks like. So I'm going to minimize that real quick. I'm going to keep going. So this is where I do some more data engineering. And then finally, I train my naive Bayes algorithm. I import my libraries, and then I have my model. So I'm actually going to run my data engineering step. Okay. I think I forgot to run one particular. So now that I've run this, I can then, finally, I can now run this. Excuse me, I don't think it ran. So now that I've pressed enter, it's going to run. Okay, now that it's running, so you can see, Databricks has a pretty good UI. It can actually help you troubleshoot some of the stuff that goes on. I think I just executed the blocks in the wrong order. So now that I've executed, it looks like I do have to do the calculate the one L1 statistics. Essentially, training and test data, those two variables are being used later on. So it's calculating that. Now I can run it over here. I can do the data engineering, and it's sending that to cluster. It's running the command. Now it's working. And after that's done, then you can just train the naive Bayes algorithm. Now it's very easy to train, and it's actually very quickly. You can train the data. Once you put it in the right format, it's just one line of code. So we have to wait for this to finish up. After it's done, then we can execute this, and then you run the command, and you'll notice it trends. It basically trains over the data, and it does a fairly quick, very good job of just learning from the data very quickly. And that has to do with the specific algorithm. But as we can see, it's very effective. And then from there, you can generate your confusion matrix on your test data. So I only took my test data here, my test data frame, and then I got the real answer and I knew the prediction. And then I was able to fill out my confusion matrix. Now, the decision tree, it takes a long time to train, but this is the code for the decision tree. And then this is how you can generate the confusion matrix from the decision tree. Okay, so that's the demo. I'm just going to briefly talk about lessons learned, and in particular, some of the main lessons learned were that working with Spark is fairly straightforward if you have worked with Pandas or Python before. I thought, well, it's not a hard if, but my experience with Pandas did help me understand a little bit about the data sets and how we can manipulate the data frames in particular. If you're familiar with statistical models, working with Spark is also very, very easy to work with because you've used other languages or tools. And then, in short, it is a tool that a data scientist should know at a high level. There was some trouble converting between data frames when I was doing this project, RDDs, and using some of the API. So you have to be careful about what documentation you're reading and what version it refers to. Lastly, you have online FAQs and developer forums. They might be talking about specific functionality that may or may not have been removed. So you kind of have to double check and make sure that you're reading information that is going to apply to your particular version of Spark. Now, for Python, since you saw that I was only using Python for the code, you can use other libraries with Spark, excuse me. So you can use, as you saw, I was using NumPy and Pandas as well. So you just import those libraries. And lastly, decision trees can take significantly longer to train than Bayes, at least for MLlib. And that also might have to do with how I was training my data. In short, I learned a good amount about Apache Spark, as I was doing this project, I really appreciate the stuff I've learned this entire semester related to big data technologies. I had a great time. I think the class has some challenging but exciting projects that help you, focus your and basically sharpen your skills when it comes to development, software development, and also big data processing. So thank you very much for the time. Have a good one. Thank you for the semester. Take care.